Hello, my name is Robin Cleveland and I'm in the Institute of Biomedical Engineering at the University of Oxford. And I'll be giving this a ThUNDDAR live talk on ultrasound propagation, the fundamentals. And this is the second talk on ultrasound propagation fundamentals in this series. So again, just to recap on the motivation for this, in therapeutic ultrasound, we typically have an ultrasound transducer outside of the body. It's coupled to the body using a coupling medium, often water, and then the ultrasound waves have to pass through skin, other areas of soft tissue, fat, for example, into the organ of interest, and then focus into the treatment site, which is where we get the high intensity region and where we get the therapeutic effect that we're interested in. And there are multiple phenomena that go on in describing the acoustic waves that pass through that. In the first series, the first episode in the series, I gave an introduction to the wave equation, impedance and intensity, reflection, refraction, and impedance. In this second part, I will talk about attenuation, diffraction, and focusing, and some solution for some typical canonical ultrasound sources. So first, let's go on to attenuation. So if you have an ultrasound wave and you generate it with a transmitter, if you had a plane wave, and what I talked about in the first part of this series, where we had plane waves, as that wave travels through the tissue, it won't change in amplitude. And if we picked it up with a receiver, we'd get all of the energy. But in reality, as that wave passes through, some of that energy is lost. And it's lost through two mechanisms. First is what's referred to as absorption, and that's actually conversion into heat. So we leave a little bit of heat behind in the tissue as the ultrasound passes through. And the second is scattering. Because tissue is not homogeneous medium, it's got lots of structures in it, going from organ type structures all the way down to cells and then intercellular components. Those changes in the properties will result in scattering or reflection, and that will take energy being directed out of the beam elsewhere, which will be again perceived as a loss of signal. And together, the loss of signal in both absorption and scattering are normally added together into what's referred to as attenuation. And what we find is, as we take a receiver and we move it away from a source, is that the amplitude decays exponentially, right? So we have this exponential form. So if P naught is the pressure at the transmitter, as we move the receiver away, the pressure at some distance x from the transmitter decays away exponentially. And this is often referred to as Beer's law or the Beer-Lambert law in optics, and is common for many wave processes where you have this exponential decay in amplitude. So for example, if you have a 1 megahertz transducer and you looked in space at what the waveform looked like, it would oscillate up and down, but the amplitude would decay. And note that the frequency won't change, but the amplitude changes, and this is due to attenuation, due to energy being removed from the wave. And kind of a typical value at a megahertz in soft tissue is an absorption coefficient alpha of 5 nepers per meter, which means that the pressure will drop to 1 over E, or 37%, at 0.2 meters, or at 20 centimeters. This effect is frequency dependent, and tissue attenuation increases normally linearly, or at least with a power law as we go through tissue. So the common formula you might see for absorption in tissue is alpha as a function of frequency is some constant times F over a reference frequency to the power of N. Normally in ultrasound, the reference frequency is 1 megahertz. So alpha 1 is typically an absorption that's reported at 1 megahertz. And then the power law is most commonly taken to be N equals 1, although if you actually look at the data, a lot of the data for most soft tissues falls between 1.1 and 1.3. But using N equals 1 is normally pretty good if you're covering a small range of frequencies. And sort of typical values for tissue, soft tissue, so kidney, and has a value of about 3.7, fat 7.2, muscle 15. And these properties will have a lot of variance in them. I talked a little bit about that to do with sound speed, but actually if you look at absorption properties, they vary even more strongly. Often there's anisotropy. So for example, in muscle, the absorption across the fibers will be different from the absorption along the fibers. And then within soft tissue, skin has typically the highest absorption with a value of about 38. And sort of a typical average value, if you look over most soft tissues, is about 5.8 nepers per meter for absorption. And so what that means is you go higher up in frequency, the signal will decay more quickly. So if you go back to that case I showed on the previous slide, 1 megahertz with an absorption coefficient of 5 inverse meters, it dropped in 20 centimeters to 37%. If you increase up to 2 megahertz, then the alpha will double. And so now the pressure will drop to that 37% in just 10 centimeters and still. And every time you increase the frequency, you're going to mean that the signal is going to be absorbed in a shorter and shorter distance. And for imaging, this is a limit on how far deep we can penetrate inside the body. High frequencies normally give a better image, but they don't allow us to go very deep into the body because the energy is absorbed. And in therapeutic ultrasound, the trade-off is that energy that's being absorbed actually can be used into heating. But if we absorb all the energy before the target site, then we can't get any effect that we'd like. In soft tissue, so the units that I've used so far are nepers per meter, which is useful if you're using this exponential form. And that's normally what I prefer. So now attenuation coefficient I normally talk about is in terms of nepers per meter. Nepers is a dimensionless unit, kind of similar to radians, if you like. And so this product up here then will be dimensionless, and you can then calculate the pressure at any other distance. But often you'll see in ultrasound, attenuation is actually given in units of decibels per centimeter. And that comes from the idea of measuring an insertion loss. And insertion losses are typically measured in terms of decibels. So a decibel is defined as 10 times a log base 10 of a ratio of intensities or powers. So the insertion loss then is 10 times log 10 of the acoustic intensity at a distance x divided by the acoustic intensity at the source. And if you recall from the previous lecture, the intensity goes as the pressure squared. So if we put pressures in here, the squared comes outside to give us a 20 outside. That's 20 times the log of the ratio of the pressures. And then if we say that the pressure follows this exponential form, then we can get that the insertion loss is alpha times distance x times 20 log 10 of E. And so the attenuation that you can get in dB per centimeter is this insertion loss divided by x to get rid of the x. It's this term here. And that turns out to be 20 log 10 of E times the alpha that was appeared in this form here. So alpha bar in dB per centimeter is related to alpha in nepers per meter using this formula here, where the 20 log 10 E is the factor that gets you from one to the other. So if you put the numbers into that, it turns out that 1 neper per meter is a 0.0868 dB per centimeter. So that's a good conversion factor to use. And if we look at an example of that, for example, the average value I gave at 1 megahertz for tissue is at 5.8 nepers per meter. So if we multiply that by this scaling factor of 0.08686 dB per centimeter per neper meter, then that comes out to about half a dB per centimeter. So roughly absorption in tissue at 1 megahertz, about 5 or 6 nepers per meter, about half a dB per centimeter. Now, when you have attenuation, we often have dispersion as well. And so dispersion refers to the fact that different frequencies travel at slightly different velocities or different sound speeds. And the relationship that can be used to determine that is what's referred to as the Kramers-Kronig relation. And so if you assume that your system is causal, so no output happens before an input goes in, then actually means that attenuation and dispersion are not independent of each other. They're actually linked to each other. And there are 2 papers in here where this has been shown for this power law form of attenuation. You can then calculate what the sound speed is. In general, for n not equal to 1, then the expression takes this form here. For the special case when n equals 1, the attenuation the sound speed as a function of frequency takes this form here. And for the case when n equals 2, there's actually turns out that there's no dispersion. The n equals 2 case is common for things like water, very simple fluids. And so those tend to be dispersion free. So all the different frequencies travel at the same velocity. But for things like soft tissue, then you will actually have variations in sound speed. And so if we look at the n equals 1 case, what that means, so this is, I'm plotting here as a function of frequency. This is 1 megahertz here. 10 megahertz on the right-hand side, and 100 kilohertz down here. I've set them all to be at 1540, which was our sort of average sound speed at 1 megahertz. And then depending on the strength of the attenuation, the dispersion will vary. So if you're at 0.3 dB per centimeter, so it's a little less than the average soft tissue, then you get about a 2 meter per second change over this 2 orders of magnitude. And to start getting significant changes in sound speed, you really need to have much higher attenuation. So the effect is there. In many cases, it's small, but for some important cases, that may so in cases where you're very worried about slight changes in the sound speed, these effects could potentially be important. Right, so now we're going to go on to looking at acoustic sources and the diffraction that happens when we have them. So most acoustic sources that are used for ultrasound use piezoelectric sources. So this is a flat, unfocused transducer. It's a piezoelectric disc in here. You put a voltage across it, and it changes its thickness. And as you oscillate the voltage, the thickness goes backwards and forwards. And so you actually get a velocity source where at that piezoelectric material. On the right here, this is also a piezoelectric transducer. In this one here, it's been curved so that it creates a natural focus at the radius of curvature of the curvature of this bulb. And these are the 2 most common sources that are used in biomedical ultrasound. All right, and so if you want to calculate the pressure field, if we have a disk here that's moving with a velocity u, then you can work out a little area on the surface. We would call that xs and ys for the source location in this plane. And if we want to know the pressure at some location x, y, and z, then we have to work out the acoustic field that comes from this particular point based on that distance. And then we integrate over the entire surface to get the entire pressure field. So the pressure field is the velocity at that surface. We delay the field by a t minus r over c. So that's to allow the wave to propagate from here out to this point here. And we assume spherical spreading, which means we have a 1 over r effect. And then when you put that into the math, it turns out you need a rho naught over 2 pi scaling factor up front to make everything work out just right. This is commonly known as the Rayleigh integral. And so it means that if you know the particle velocity anywhere on a surface, you can work out the pressure anywhere in space if you can do this 2D surface integral. If you don't, this is for an arbitrary, you can take any time waveform. So this holds not for any waveform that you want to put in. And often in imaging where short pulses are used, this is a common formulation to use. In the case where your wave is time harmonic, so it's at a single frequency, then your source condition has the time dependence is going to be e to the minus I omega t or e to the plus j omega t, depending on whether you're a physicist or an electrical engineer or some funny mix in between. So I'm using e to the minus I omega t here. And when you put that into that formula, then the e to the minus I omega t comes out. This u dot here, this is actually the derivative of the velocity. That gives you an I omega coming out front. And you get this integral here, which is often referred to as the Rayleigh-Sommerfeld integral. But again, it's a surface integral that allows you then to calculate the pressure anywhere. So in a few cases, for transducers we use, there are some exact solutions that we can make use of. So the first one is for an unfocused, for a flat piston source. That's in a baffle here. So the baffle is a green object. That means that there's no fluid motion here. So it's like putting it in a rigid plane. And if you allow this transducer to move, and so it has a velocity associated with it as it moves, then the pressure that we get anywhere on axis is the sum of the wave that appears to come from the center. So this is the waveform that when this transducer moved. And then you get an edge wave that appears to come from the edge of the transducer that's flipped upside down, and it's delayed by the distance where the edge of the transducer is. So actually the pressure anywhere on axis is the piston velocity, time delayed by t minus r over c naught. That's the distance from the center of the transducer. And then a minus sign here because you have this edge wave. It's the same waveform shape, and it's delayed depending by the distance to the edge. And so if you're at a point close to the transducer, you can actually often see these 2 things distinctly. You see the center wave coming, followed by an edge wave. As you get further away, the distance, the path distance between the center and the edge becomes smaller and smaller, and these 2 waveforms will actually start to overlap. Okay, so this solution will work anywhere on axis for any type of waveform that you put into the transducer. I won't go through the details, but if you go off axis, then it turns out as you move off axis, you have a bunch of little circles that are complete, and then you have some circles aren't complete, and so you've got to break up the solution into two cases in that case, and then you can actually write the pressure as a convolution between the particle velocity and then an impulse, what's referred to as a spatial impulse response, which is the field you get if you put a delta function into the source condition. And this paper back from Harris from 1980s by Jerry Harris actually gives the analytical expression for that impulse response for a circular transducer. So I won't go into the details, but it's there if you want to make use of it. For an unfocused piston, if you're in the frequency domain, this is the Rayleigh-Sommerfeld integral, then the pressure field we get, this is an example of a pressure field from a 2¼ megahertz transducer with a diameter of 10 millimeters. And you can see that the field that is generated here, and I've shown it both in axial and radial direction, you can see you kind of get a beam of sound that comes out, but that it gets spread out in different directions as well. So it's not just a plane wave, we actually have a much more complex field associated with that. We have a region near the transducer, which is where the energy is collimated. And note it's not a plane wave in here, we don't have nice flat waveforms, we've got a very complicated pressure structure, but the sound is sort of collimated. And then at some distance, it starts to undergo a transition to what looks like spherical spreading. Okay. And so if you actually, we have an analytical expression along the axis in this case, so you can take that case I gave you for the on-axis solution in the time domain, put in a sinusoidal waveform, and then you can calculate an exact on-axis expression for the pressure field. And if we look at the amplitude as a function of distance, the amplitude as a function of distance away from the transducer is 2 times the source pressure, and then it's the sign that depends both on the distance you are and on the radius of the transducer. And if you like, this is the wave associated, this is the signal associated with the edge wave, this is the signal associated with the center wave. And if you plot this as a function of distance, you see in the near field that the pressure oscillates between 0 and 2. And this has been normalized by the source pressure. 1 would be if it was a plane wave. If there was no diffraction or any other effects going on, it would just be 1. So sometimes it becomes double, sometimes it becomes 0. You can see this oscillation. It reaches a peak here and then decays away with distance. So after you get over this peak, and the decay here just will go on, and somewhere out here, and it's your call as to where you say it's close enough to spherical spreading, but it starts to approach a case that's referred to as spherical spreading. And this is a definition here. I give it this distance where it last crosses 1 is referred to as the Rayleigh distance. And for a circular transducer, the Rayleigh distance is 1/2 times the wave number k times a squared. And that's actually the same as pi a squared over lambda. So the ratio of the area of the transducer to the wavelength of the sound. And that's commonly what I use as the distance for where it truly goes to spherical spreading. Although many people will identify that it looks like it's spherically spreading before that, and will take the distance as some location earlier in as well. Okay, and that solution I gave you there is actually, there's not quite an exact solution for everywhere, but the Rayleigh-Sommerfeld integral can be done off axis, and you can turn that 2D surface integral into a 1D line integral, given in this form here, originally published by Hutchins in the 1980s, republished in 1999 as well in JASA, which allows to get the field everywhere. And actually those plots I showed you on the previous figure came from putting this into MATLAB and just solving that integral. But in therapeutic ultrasound, we often use focused transducers rather than just the flat surfaces. So I showed you that picture of that bowl, which has got a curved surface here, and using R sub c as the radius of curvature, and it has a radius of the aperture A. So it now, rather than having a single number, it has 2 numbers associated with it, the geometrical focusing area radius and the radius of the aperture. And again, on axis, it turns out there's a solution. It's referred to as the O'Neill solution. It tells us the pressure as a function of distance along the focus here. It's given in this case here, rho naught, C naught, U naught being the amplitude of the frequency. F is the same as RC. Sorry, just changed my terminology here. So F is the same as RC. Up here, Z is the distance from the back of the transducer, so along this axis here. And R max is the distance from your observation point to where the edge of the transducer is, and it's given by this expression here. Okay, and if you plot the pressure as along the axis when we have a focused transducer, here is an example of one 70 millimeter focal length, frequency of 3.5 megahertz, and this one has a radius of 7.5 millimeters or a diameter of 15 millimeters. And I've plotted from 20 millimeters away from the back of the transducer out to 120. And so you can see you have some oscillations here. The pressure goes up, reaches a peak, and actually, if you notice the peak here, it's about 55 millimeters, right? Even though the radius of curvature was 70. So 70 millimeters here, the pressure's actually dropped down. And so for a focused transducer, this is an effect we commonly see, is that the peak pressure actually occurs a little bit in front of where the geometrical focus is. Okay. And then the pressure now has reached, if you remember, for an unfocused transducer, you got oscillations up to 2. For this, we've got much higher. And actually, at the focal distance here, at 70 millimeters, the pressure was 5.9 times that of the pressure at the source. So this is referred to as having a focusing gain of 5.9 because of that ratio. And actually turns out, if you look at the O'Neill solution, you can calculate what the pressure is at the focus on that solution. And it's related to the source condition times this G. And when you do the algebra on it, then the focusing gain is the Rayleigh distance for that transducer, if it was an unfocused transducer, divided by the radius of curvature. And so the gain of our transducer depends on this ratio of the Rayleigh distance of the transducer to the radius of curvature that you use. And so it's going to depend on things like the aperture. So if I, for example, if I increase the aperture from 7.5 millimeters out to 15 millimeters, then I will have doubled the radius. I get 4 times the gain. And so now this is the pressure, and this again going from 20 to 120 millimeters. We see many more oscillations now in the near field, and now the pressure building up to a value that's almost 25 in and around the focus. And you can see now that the peak has shifted. It has got quite close to 70 millimeters. Here it was more like 55, and here it was 70. And you can actually, the approximate formula for where the maximum occurs is at the radius of curvature, and then 1 minus 12 over g squared. So it depends on the gain. In the case here where the gain was about 6, that means you get 1 minus 12 over 36. So it's at about 2/3 of the focal length, which is at 55 millimeters. By the time you get to a gain of about 24, this effect becomes quite small, and it's almost right here at the radius of curvature. And if we go up again in size, so now go up to 20 millimeters, now I've got the gain up to about 42. And we have a nice high peak here, almost right on at 70 millimeters. We've got this nice near field in here. We've now got a very tight focus. And so by changing the size of the transducer, we've managed to get a much higher gain, going from 6 up to 42. And if you could see the focal spot here, which was quite, if you take the focal spot as where the half pressure points are, it's quite large. It covered here more than about 80 millimeters or so. Here we've been able to reduce the focal spot size down to about 20 millimeters. So larger transducers tend to give us much tighter focal spots for a focused transducer. And in reality, what we want, if you want a highly focused transducer, we want the gain to be large. Normally, the radius of curvature we don't have a lot of control over, because that's going to be at the depth at which we're trying to treat. So that will depend on where our target location is. So the two things we have to play with are the frequency, which changes K, and the aperture size that changes A. And if you want a large gain, you want to have a Rayleigh distance much bigger than radius of curvature. You want to have the largest radius A that you can possibly have, and the highest frequency that will allow you to deliver to the distance that you're interested in as well. So those are the axial fields. Actually, across the field, O'Neill came up with a solution across the field as well. And so if you're at the geometrical focus, so there's not at the peak pressure, but that's where the geometrical focus occurs, then the pressure as a function of y, that's the off-axis distance here, it goes as J1 of KAY over RC over KAY over 2RC, where J1 is the Bessel function of the first order. And so if we plot for two of the cases I showed previously, again, this is the 70mm transducer at 3.5 megahertz. For a 7.5 millimeter diameter radius transducer, then we have this high on-axis pressure, and then it decays away with J1x over half x. And by about, you get a null at about 2 millimeters, and then we get some little side lobes, some little wobbles on the side out beyond that. If you change to 15 millimeters, and it looks almost the same, but if you notice down on the bottom here, the horizontal axis has gone from 10 millimeters here to 5 millimeters here, so we've actually squished the field in. So by making a higher sized transducer, we got a better focusing gain, and we got that by actually squishing the focus in laterally that is what gave us that higher pressure. So those formulas from O'Neill you can actually use to approximate the length and the width of the focal zone that's created by a focusing transducer. The axial length is 7 times the wavelength times the ratio of the focal length to the diameter of the transducer squared. And the width of the transducer, up and down, of the focal length, sorry, is proportional to the wavelength times F over D. Right, and so by changing the wavelength, you can change both of these things. And by changing F over D, right, you can, again, you also are that also gives you ability to create a tighter focus. So tight focus, you want to have a small wavelength, high frequency, and you also want to have a diameter of the transducer much bigger than the focal length. And in reality, for most therapeutic transducers, F over D is about 1, because that's, for most focal lengths, it's about the size of transducer you can get where you have acoustic windows into the body. And so for an example, for a typical therapeutic ultrasound transducer, for example, a research one that I showed you on the first slide, has a frequency of around 1 megahertz, a diameter of about 64 millimeters, and a focal length of 63 millimeters. And that means, based on this formula here, you'd get an axial length, you'd create a focal spot that's about 10 millimeters long and about 1.5 millimeters wide, which is typically what we see for many applications in therapeutic ultrasound, right? And that's actually controlled by the diffraction associated with the wave propagation from a focus source. So those are the on-axis analytical expressions. If you want a solution everywhere, then again, you can do an approximate solution. So if you're interested in a pressure field out here, and in this case here, I assume at an angle theta and at a radial distance r from the center of the transducer, then the pressure can be written in this form here, where I is an integral that depends on this function y and z. Y is this transform variable in terms of r and theta, and z is this transform variable just in terms of theta. And then I itself can be expressed as a sum of Bessel functions. So I takes this form here, it's got real and imaginary parts, and each of these things here are sums of Bessel functions. And as the series actually converges quite nicely, and in the paper here by Chen, Schwartz, and Parker, they talk about it in detail. And so you can add this up to create the pressure field anywhere from a focused piston transducer as well. All right, so that's the end of this second talk on the fundamentals of ultrasound propagation. Just to recap, absorption acts to remove energy from the sound field, and that is what converts stuff into heat. In tissue, the absorption typically increases linearly with frequency to a good approximation. And when we have absorption present, then we also have dispersion, which means that the sound speed will change as a function of frequency, although for many applications that effect can be small. For the piston sources that are typically used as ultrasound transducers, we use the Rayleigh integral to describe the pressure field that comes out from that. And we have some closed forms expressions for flat or unfocused transducers, both on axis, both in the time domain and in the frequency domain, and then approximations that we can use to go off axis. For focused transducers, it's similar. We have analytical expressions on axis and in the focal plane, so we can get estimates of the size of the focal spot that comes out of a transducer, and then expressions in terms of sums of Bessel functions to get the field everywhere. So Thank you for your attention. I hope that was helpful, and I would be happy to answer any questions that come in through the ThUNDDAR website. Thank you very much.